Okay, let's go. Number 1. Stevenson, 218, a red hypergiant approximately 20,000 light-years from Earth, sitting in the constellation Scutum. Its radius is roughly 2,150 times the radius of our Sun. That number is difficult to hold, so here's what it means in practice. If you replaced our Sun with Stephenson 218 and placed it at the center of our solar system, its surface would extend past the orbit of Saturn, not close to Saturn, not to Saturn, past it. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, all of them would be inside the star. You would need to travel beyond the sixth planet from our Sun to reach what would count as the star's visible edge. Our Sun, for comparison, has a radius of about 700,000 kilometers. You could fit roughly 1.3 million Earths inside it. That number is already beyond what most people can picture. Stephenson 218 has a radius 2,150 times larger than that. Its volume is so much greater than the Sun's that if you tried to fill it with copies of our Sun, you would need approximately 10 billion of them. Here is the number that ends the first paragraph of this list. The surface area of Stephenson 218 is roughly 18 million times greater than the surface area of the Earth. If you took every ocean on this planet, all the water in the Atlantic, Pacific, Indian, Arctic, and Southern Oceans combined, and spread it across the surface of this star, it would cover a region smaller than a rounding error. The entire surface of the Earth, laid flat against this star, would be geometrically invisible. And Stephenson 218 is still just a star. One object, one point of light in a galaxy containing between 100 and 400 billion of them. It is the largest entry on this list, and yet it doesn't come close to what comes next. What happens when you build something out of stars, columns of them, nurseries of them, structures that span not kilometers or AU but light years? Number 1 is a star. By number 4, stars won't be a useful unit of measurement anymore. Number 2, the pillars of creation. In April 1995, the Hubble Space Telescope turned toward a region of the Eagle Nebula, 6,500 light-years from Earth, and produced one of the most recognized images in the history of astronomy. 3 columns of dark gas and dust rising against a glowing backdrop of illuminated hydrogen, their surfaces being slowly eroded by intense radiation from nearby newborn stars. The image appeared on the front pages of newspapers. It ended up in textbooks, on posters, in museums. It became a symbol of what space looks like when you have a good enough telescope to actually look. Almost none of the people who have seen that image know how large those columns are. The tallest of the 3 pillars is approximately 5 light-years from base to tip. 5 light-years, 47 trillion kilometers. To help with that number, consider our own solar system. The Sun's gravitational influence extends to a vast shell of icy bodies at the outermost edge of the solar system, called the Oort cloud. The Oort cloud begins roughly 2,000 astronomical units from the Sun, 1 astronomical unit being the Earth to Sun distance, and extends out to perhaps 100,000. That outer boundary, where the Sun's gravity fades to near nothing and interstellar space begins, sits approximately 1.5 light-years from Earth. Our entire solar system, from the Sun to the very edge of its gravitational reach, spans 1.5 light-years. 1 pillar of creation is more than 3 times that length. If you placed our Sun at the base of the tallest pillar and drew a circle extending to the absolute frontier of its gravitational influence, to the point where our solar system ends and interstellar space begins, that circle would reach barely a third of the way up the column. Everything within the solar system, 8 planets, hundreds of moons, billions of comets, the Kuiper belt, the scattered disk, the entire Oort cloud, every object gravitationally bound to our star, all of it fits inside the bottom third of a single pillar of gas in an image most people treat as a pretty screensaver. Inside those pillars, stars are forming. We're forming. More precisely, the light reaching us left 6,500 years ago, so what we're observing is the past, not the present. Here's what the present may actually look like. In 2007, the Spitzer Space Telescope observed the Eagle Nebula in infrared wavelengths, and what it found was a bow shock, the remnant of a supernova explosion moving through the region. Scientists calculated the timing. That shock wave almost certainly reached the pillars of creation approximately 6,000 years ago. If the calculation is correct, the columns in that famous image have already been destroyed. The gas that formed them was scattered by the explosion of a nearby star at a moment roughly contemporary with the construction of the first Egyptian cities. We will not see the destruction for another 1,000 years, because the light confirming it won't arrive until then. You are looking at something that may not exist. You will spend the rest of your life looking at it. You will never know for certain from here. 5 light years, one structure. The Eagle Nebula that contains the pillars is itself roughly 70 light years across. The Milky Way is 87,000. The next item on this list steps outside our galaxy entirely, and what it finds there is larger, by a factor of 60. Number 3. The Tarantula Nebula. The pillars of creation are 5 light years tall. Hold that number. The Tarantula Nebula is 300 light years across. That is the jump between this item and the last one, not a factor of 2, not a gradual escalation, but 60 times larger, in a single step, and it doesn't even sit inside our own galaxy. The Tarantula Nebula, formerly catalogued as 30 Doradus, lives in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, located about 160,000 light-years from Earth. It is the largest, most luminous, and most violent star-forming region in the entire local group of galaxies. The local group is the cluster of roughly 50 galaxies that includes the Milky Way, the Andromeda Galaxy, and their various satellite systems. In our entire cosmic neighborhood, every galaxy we know of within a few million light-years, the Tarantula Nebula is the most extreme stellar nursery in existence. Here is the number that puts the size in terms you can hold on to. If the Tarantula Nebula were as close to Earth as the Orion Nebula, which sits at a comparatively nearby 1,344 light-years away, it would cast shadows on the ground at night, not glow faintly on the horizon, not be a striking object in a telescope, cast shadows. It would appear in the sky roughly 60 times larger than the full moon, and bright enough that you could read by it on a clear night. The only reason you have never experienced this, the only reason it appears in Southern Hemisphere telescopes as a faint smudge rather than a second sun, is that it sits 160,000 light-years away instead of 1,344. At the core of the Tarantula Nebula is a dense young star cluster called R136. Within that cluster, some of the most massive stellar objects ever confirmed. R136. A1 has an estimated mass of 150 to 200 times the mass of our Sun, a figure near the theoretical upper limit for stellar mass, beyond which radiation pressure would blow the star apart before it could fully form. Stars of this size release ultraviolet radiation at rates that physically blast the surrounding gas and dust outward at millions of kilometers per hour. The structure of the nebula, the tendrils and filaments visible in telescope images, is the direct result of that radiation pressure sculpting the cloud from the inside. The tarantula is being shaped by the force of its own contents. The nebula has produced in excess of 800,000 stars. Our galaxy's own star-forming regions, the Orion Nebula, Rho Ophiuchi, the Carina Nebula, are modest by comparison. The Milky Way's star formation is diffuse, spread across its disk, producing clusters of a few hundred or a few thousand stars at a time. The tarantula does something categorically different. It is not a feature of our galaxy's ecosystem. It is a reminder that our galaxy's ecosystem is, by the standards of the local group, unremarkable. We live in the quiet end of a neighborhood that contains this. 300 light-years is still, in the register of this video, a local detail. You could fit the Tarantula Nebula inside the Milky Way more than 290 times. What comes next does not fit inside galaxies at all. What comes next is attached to ours, was erupting from our own galactic center, and we had no idea until 2010. Number 4. The Fermi Bubbles. This is where the rules change. Not as a figure of speech, structurally. Everything before this section was an object out there, a star, a nebula, a structure you could point a telescope at, identify, describe from a position of distance. You are the observer. The thing is the observed. That relationship is about to end. The Fermi bubbles do not sit at some safely distant location in the universe. They are attached to the Milky Way. They extend above and below the galaxy you live in. They are, in the most literal sense, part of your home, and you didn't know they existed until November 2010. The Milky Way is a flat disk of stars and gas approximately 87,000 light-years across and a few thousand light-years thick. At its center sits Sagittarius A star, a supermassive black hole with a mass 4 million times that of the Sun. The galactic core region is dense, hot, and chaotic star formation, stellar collisions, enormous gravitational forces, and erupting from that center, extending above and below the disk, two enormous lobes of high-energy material, the Fermi bubbles. Each one is roughly 25,000 light-years tall. Combined, a total span of 50,000 light-years, stretching from well above the galactic plane to well below it. A structure more than half as tall as the galaxy is wide, anchored at the center of the galaxy we orbit. The discovery was made by Meng Su, Tracy Sladier, and Douglas Finkbeiner, analyzing data from NASA's Fermi Gamma Ray Space Telescope. In the gamma-ray sky, a map of the universe at photon energies, invisible to human eyes, two symmetric structures emerged on either side of the galactic center. Bright, sharp-edged, expanding outward at approximately 1,000 kilometers per second. The team published the discovery in 2010. The astronomical community spent several years confirming what they were looking at was real. Something created the Fermi bubbles. The universe doesn't produce 50,000 light-year structures without a cause. Two leading hypotheses have been proposed. The first, an intense period of star formation near the galactic center, which produced enough stellar winds and supernova explosions to collectively drive the surrounding gas outward into these enormous lobes over millions of years. The second, Sagittarius A star itself. The central black hole may have entered an active feeding phase, consuming gas and dust at a high rate, converting a fraction of that mass into energy, and releasing that energy as jets or winds that inflated the bubbles from within. Current evidence suggests the event occurred somewhere between 1 and 8 million years ago, before Homo sapiens, before our genus. Whatever happened at the center of the Milky Way happened in a geological era that predates the existence of human beings, and we are only now reading the aftermath in gamma rays. Here is what makes this particular kind of large unsettling. You cannot see the Fermi bubbles with your eyes. They emit gamma rays and X-rays wavelengths our visual system has no capacity to detect. They are not faint, they are not dim, they are simply in a part of the electromagnetic spectrum that evolution never gave us access to. If you could see gamma rays, the Fermi bubbles would dominate the sky. Two enormous structures, one above and one below the galactic center, clearly visible from Earth, unmistakable. Instead, you look up at night and see nothing where they are. The galaxy appears the same in that direction as in every other. Two 25,000 light-year structures attached to your galaxy, expanding outward at 1,000 kilometers per second, radiating energy continuously, and from the surface of this planet, with your eyes they are completely invisible. We knew about them for 16 years before you started watching this video. We had no idea they existed before that. Number 5. The Sloan Great Wall. The Milky Way is 87,000 light-years across. The Fermi bubbles extend 50,000 light-years above and below it. Those numbers, at this point in the video, might feel large. Hold them in mind. The Sloan Great Wall is 1.4 billion light-years long, not 1.4 billion kilometers, light-years. 1.4 billion of them. The number should require a moment. In 2003, astronomers working with the Sloan Digital Sky Survey, a systematic mapping effort that cataloged the positions of nearly 1 million galaxies, found something in the data they hadn't been expecting. A filament of galaxy clusters, connected by gravity, arranged in a wall-like structure that stretched 1.4 billion light-years across the sky. When the paper was published, it became the largest known structure in the observable universe. It held that record for a decade. Here is what 1.4 billion light-years means in practice. You enter at one end. You are traveling at the speed of light, 300,000 kilometers every second. The absolute speed limit, the laws of physics impose, on anything carrying information through space. Nothing with mass can actually achieve this speed. This is a thought experiment about the structure's scale, not a description of a journey you could take. You travel without stopping, without slowing, at this maximum velocity, for the entire crossing. You exit the other side 1.4 billion years later. The universe, when you entered, was in roughly its current state. The universe, when you emerge, will be 1.4 billion years older, a span of time comparable to the gap between the present day and the earliest complex multicellular life on Earth. Stars that existed when you entered will have exhausted their fuel, swelled into giants, shed their outer layers, and collapsed into white dwarfs or neutron stars. Entirely new generations of stars will have formed, burned, and died. Planets will have formed around those stars, and you will only just be stepping out the other side of one cosmic structure. You could fit approximately 16,000 Milky Way galaxies, placed end to end, across the length of the Sloan Great Wall. At Voyager 1's current speed, 17 kilometers per second, the fastest sustained velocity any human-built object has ever achieved. Crossing it would require approximately 24 quadrillion years. The current age of the universe is 13.8 billion years. To cross the Sloan Great Wall at Voyager's speed, you would need a duration approximately 1.7 million times the age of the universe. That is the number. That is one structure. The Sloan Great Wall is not a solid object. It is a filament, a gravitational strand of matter along which gas has collected over billions of years, galaxies have formed, and clusters of galaxies have grown and merged. It is a thread in a much larger architecture, which we'll return to near the end of this video. But as a standalone structure, identified in a single galaxy survey, holding its record for a decade before anything larger was confirmed, the Sloan Great Wall was, for a time, the definition of as large as a thing can be. Then they found something that made it look like a detail. Number 6. The Hercules Corona Borealis Great Wall. The Sloan Great Wall is 1.4 billion light-years long. The Hercules Corona Borealis Great Wall is approximately 10 billion light-years across, 7 times larger. And according to the standard model of cosmology, it should not exist. That is not hyperbole. That is the actual scientific tension this structure creates. The cosmological principle, one of the foundational assumptions of modern physics, states that on sufficiently large scales, the universe should be homogeneous and isotropic, smooth, in other words. No single structure should organize matter at scales greater than roughly 300 million light-years. Below that threshold, gravity has had time to cluster things. Galaxies form, filaments develop, walls like the Sloan Great Wall emerge. Above it, in a universe the age ours is, with gravity operating as we understand it, large-scale structure should average out. The cosmos should look the same in every direction, at every sufficiently large scale, because there simply hasn't been enough time since the Big Bang for gravity to organize matter more extensively than that. 10 billion light-years is not 300 million. It is 33 times larger than the scale at which, by our best current theory, coherent structure should stop being possible. The structure was identified in work published between 2013 and 2014 by a team led by the Hungarian astronomer István Horváth, using a method that wasn't mapping galaxy positions directly. They were mapping gamma-ray bursts. These are the most energetic explosions in the universe, the deaths of massive stars, releasing in seconds more energy than our sun will emit in its entire 10 billion-year lifetime. Gamma-ray bursts trace massive star deaths. Massive star deaths trace where massive stars live. Massive stars live in galaxies, and galaxies cluster where matter concentrates. By analyzing the distribution of gamma-ray bursts across a broad region of sky, the team found a statistical excess, a zone where these events clustered significantly more densely than would be expected if the universe were smooth at that scale. That zone spans approximately 10 billion light-years. 10 billion light-years. The observable universe has a diameter of 93 billion light-years. This single structure, if it is a structure, spans roughly 10% of everything we can observe. Some cosmologists dispute the classification. The argument is that gamma-ray bursts, as a tracer population, introduce sampling biases. The clustering may reflect the limitations of the dataset rather than the presence of a genuine coherent structure. Others stand by the analysis, arguing the statistical signal is robust and the clustering is real. The debate continues in the peer-reviewed literature, which is exactly where it should continue. But here is the thing about both possible outcomes. If the Hercules Corona Borealis Great Wall is a real physical structure, our model of how the universe evolved is wrong, or incomplete, at the largest scales. Something organized matter across 10 billion light-years in a universe that, by our calculations, has not existed long enough for gravity alone to do that. We are missing a mechanism, a process, or a piece of physics that our current framework doesn't contain. If it is not a real structure, we do not have reliable enough observational tools to accurately map the universe at its largest scales, and the structures we've been identifying may be artifacts of incomplete data. We are getting the map wrong in ways we can't currently detect or correct. Both possibilities are uncomfortable. Neither has a clean resolution yet. And we haven't reached the largest one yet. Number 7. The Laniakea Supercluster. In 2014, a team of astronomers published a paper in the journal Nature and quietly rewrote the home address of every living thing on Earth. Not the street, not the city, not the country, or the continent, or the planet, or the solar system, or even the galaxy, the supercluster. We had been writing the next level of our address wrong, and we didn't know it, because we had never been able to read it. The discovery was made by R. Brent Tully, Helene Courtois, Yehuda Hoffman, and Daniel Pomerede, and the key to it was a shift in methodology. Previous surveys had mapped large-scale structure by recording galaxy positions where galaxies are in space. The team went further. They mapped how galaxies move, the subtle drift and flow of tens of thousands of galaxies, each one responding to the gravitational pull of everything in its cosmic environment, forming vast currents that trace the underlying landscape of mass. When they charted those flows, what emerged was a pattern. Our galaxy, and Andromeda, and tens of thousands of other galaxies across an enormous region of space were all participating in the same gravitational motion, streaming together toward a common center, like water moving downhill toward the same river basin, regardless of where it started on the hillside. They called this basin Laniakea. The name is Hawaiian for immeasurable heaven. It was suggested by a Hawaiian language professor in honor of the Polynesian navigators who once crossed the Pacific using nothing but the stars, people who found the ocean by reading the sky. The choice felt right. We had just found out how deep the ocean is. Laniakea contains roughly 100,000 large galaxies. It stretches 520 million light-years across. Our position within it, the Milky Way, the Andromeda Galaxy, the entire local group of about 50 galaxies, sits near the outer edge of Laniakea, like a small town on the outskirts of a continent we didn't know we were on. You could fit approximately 5,900 Milky Way galaxies across its diameter. At the gravitational center of Laniakea is a region called the Great Attractor. For decades, astronomers had known something was off. Galaxies in a broad region of space around us were drifting in the same direction toward something massive, something generating enough gravitational pull to redirect the motion of tens of thousands of galaxies across hundreds of millions of light-years. They could measure the pull clearly. They could not see the source. The Great Attractor sits in a direction that places it directly behind the plane of the Milky Way, hidden by our own galaxy's gas and dust, obscured from optical observation by the structure we live inside. They could feel the gravity before they could see what was causing it. Like standing in a current and knowing the river is running downhill, without being able to see where the slope leads. The Great Attractor is now understood to be centered around the Norma cluster and several neighboring overdense regions, approximately 250 million light-years away. We are moving toward it, embedded in the broader Laniakea flow, at roughly 600 kilometers per second. That motion has been ongoing since before the Earth existed. You have been inside Laniakea your entire life. Every human who has ever lived has been inside it. Every civilization that ever built a telescope, observed the sky, charted the stars, theorized about the structure of the cosmos, all of them were inside it. And we didn't have a name for it, didn't know its boundaries, didn't know the shape or extent of the thing we were embedded in until 11 years ago. What else are we inside that we haven't named yet? Number 8. The South Pole Wall. The Milky Way has been hiding things. Not passively, not by being too faint or too distant, but by existing by sitting in our line of sight and blocking whatever lies behind it with 100,000 light-years of gas and dust. There is a formal term for the region of sky our galaxy conceals. Astronomers call it the zone of avoidance. Roughly 20% of the total sky, everything within approximately 10 degrees of the galactic plane, is obscured from standard optical observation by our own home. Whatever is behind it, we cannot see by simply looking. We are living inside the thing that blinds us. The Great Attractor sat hidden in that zone for decades. Astronomers knew something massive was there because they could see its gravitational effect on everything around it. They could not see the source. This situation, sensing a cause without being able to observe, it turns out to be more common than the history of astronomy suggests it should be. In 2020, a team led by Daniel Pomerede, using a dataset called Cosmic Flows 3 that cataloged the velocities of approximately 18,000 galaxies, announced the detection of a previously unmapped billion light-year structure they named the South Pole Wall. It extends below the southern galactic plane, partially within the zone of avoidance, partially just outside it, and stretches approximately 1.4 billion light-years in total length. Its scale is comparable to the Sloan Great Wall, which was announced in 2003 and which, at the time, was the largest confirmed structure in the observable universe. The South Pole Wall was found the same way Laniakea was found, not by recording where galaxies are, but by measuring how they move. Each galaxy has a radial velocity, a speed at which it is moving toward or away from us, detectable as a shift in the wavelength of its light. By analyzing those velocities across tens of thousands of galaxies, the team could infer the gravitational landscape of the region, where mass concentrations must exist to produce the motions observed. The South Pole Wall emerged from those flows as a dense ridge of matter, a concentration massive enough to be deflecting thousands of galaxies around it, sitting partially behind our own galaxy, invisible to conventional surveys, present the whole time. The paper's language is precise. The South Pole Wall is described as one of the most massive concentrations of matter in the nearby universe. It sits centered at around 700 million light-years from Earth. For 17 years, from 2003 to 2020, the Sloan, Great Wall, and a handful of comparable structures were what astronomers considered the known inventory of billion light-year objects in our vicinity. The South Pole Wall was there the entire time. We found it only when we developed the right dataset and the right method. The zone of avoidance remains. Approximately 20% of the sky is still concealed by the plane of the Milky Way. In that 20%, there are almost certainly galaxy clusters, filaments, and walls we cannot see, cannot map by conventional means, and cannot name. We have completed the survey of perhaps 80% of the accessible sky, and within that 80%, we are still announcing structures the scale of the South Pole Wall. The map is unfinished by definition. The obstruction is our own home, and we cannot move outside it to see past it. Whatever is in the zone of avoidance is waiting for better methods. Number 9. The Cosmic Web. Pull back far enough that Laniakea shrinks to a small feature, far enough that the South Pole Wall and the Sloan Great Wall and the Hercules Corona Borealis Great Wall are just local threads in a larger fabric, and a pattern emerges. The universe has a shape, not a random scattering of matter, not a uniform fog, not an unstructured distribution of galaxies and clusters, an architecture. Strands of material weaving through space in a web-like mesh of filaments surrounding vast empty bubbles, consistent across hundreds of millions of light-years and replicating across billions more. Astronomers call it the cosmic web, and every structure named in this video is a detail within it. The existence of this architecture was predicted mathematically before it was observed. In the 1970s, the Soviet physicist Yakov Zeldovich worked out that gravitational collapse in an expanding universe should not produce isolated spheres. It should produce sheets and filaments, flattened concentrations of matter forming along preferred directions set by the initial density fluctuations in the early universe, then intersecting at nodes where the densest concentrations accumulate. His predicted geometry looked like the foam of a soap bubble or the structure of a sponge. Thin walls surrounding vast empty regions, with the densest accumulations at the points where the walls meet. It took the galaxy surveys of the 1980s, 1990s, and 2000s to confirm that the large-scale universe actually looks like this, that the real sky, mapped at sufficient depth, matches the foam Zeldovich's mathematics described. The filaments of the cosmic web are made primarily of dark matter. Not primarily in the sense of slightly, more primarily in the sense that ordinary matter, the kind that makes up stars and planets and gas clouds and everything that telescopes can actually detect, is a minor fraction of what the filaments contain. Dark matter does not emit light, does not absorb light, and does not interact with electromagnetic radiation in any way that would make it directly observable by any telescope currently in operation. Its existence is inferred from gravitational lensing, the bending of light from distant galaxies by mass that isn't visible, and from the motion of ordinary matter within and around the filaments. We map the skeleton of the universe using the shadows it casts on things we can see. Along the filaments, gas collects, galaxies form. Clusters of galaxies gather at the nodes where filaments intersect, and between them, the voids, roughly spherical regions nearly devoid of matter, typically 100 to 300 million light-years across, their interiors almost entirely empty except for a very occasional isolated galaxy. These voids make up approximately 80% of the universe's total volume. All the matter in existence, every star, every planet, every nebula, every galaxy wall, named in this video, the entire observable mass of the cosmos occupies the remaining 20%. The material universe is the thin coating on an almost entirely empty structure. In 2005, Volker Springel and colleagues published the results of the Millennium Simulation, a computer model running 10 billion particles through the full span of cosmic time, tracking how matter evolved from the nearly uniform conditions of the early universe to the present day. The cosmic web it produced matched the observed distribution of galaxies in the actual sky with remarkable precision. The same filaments, the same voids, the same node structure. The simulation and the universe agreed. One of the great confirmations in the history of cosmology, produced by running physics on a computer for several months and comparing the output to the sky. The cosmic web spans the entire observable universe. Every structure in this video, from the Pillars of Creation to Laniakea to the Hercules Corona Borealis Great Wall, is a local detail in this larger pattern. And containing all of it, as the final item on this list, is the structure those patterns belong to. Number 10. The observable universe. You might assume the observable universe is 13.8 billion light-years across, because the universe is 13.8 billion years old, and light can only travel so far in that time. The assumption follows naturally from the numbers. It is also wrong. The universe has been expanding the entire time those photons were traveling. They set out from their sources when everything was much closer together. The matter that emitted the oldest light, we can detect the cosmic microwave background, the thermal afterglow of the Big Bang itself, was, at the moment of emission, only about 42 million light-years from what would become Earth. While those photons crossed space toward us, space itself expanded beneath them, the sources stretched away. The matter that emitted that ancient light is now 46.5 billion light-years from Earth. The observable universe has a radius of 46.5 billion light-years and a diameter of 93 billion, not 27.6 billion, not 13.8. 93 billion light-years from edge to edge, and that's just the sphere of everything we can, in principle, observe. Inside that sphere, approximately 2 trillion galaxies. That number was revised in 2016 by Christopher Consolis and colleagues at the University of Nottingham, who used Hubble Space Telescope deep field images to statistically infer the total. The previous consensus estimate was around 200 billion galaxies. The revision multiplied it by 10, 2 trillion galaxies, each containing hundreds of billions of stars, the great majority of those stars orbited by planets, the chemistry of those planets regulated by the same physics that produced every structure on this list. But 93 billion light-years is not the edge of what exists. It is only the edge of what we can see. The observable universe is bounded not by the edge of space, but by the limit of how far light has had time to travel since the Big Bang, and by how far the expansion of space has carried those sources since. What lies beyond that boundary is unknown. Possibly a universe many thousands of times larger than what we can observe. Possibly infinite in extent. We cannot know, because the light from beyond has not reached us, and will not. The observable universe is the horizon. What's beyond the horizon is not nothing. It is everything we cannot see. There is another boundary, and it is in some ways the more troubling of the two. The cosmic event horizon currently sits at approximately 16 billion light-years. That is the distance beyond which any light emitted right now at this exact moment, as you watch this, will never reach us. Dark energy is accelerating the expansion of space at a rate that outpaces the speed of those photons. They will travel toward us forever. They will get no closer. Between 16 billion and 46.5 billion light-years, there are galaxies whose ancient light is still arriving, and whose past we can still observe. but whose present state is already permanently inaccessible. They are gone from our future. We can see where they were. We cannot see where they are. We will never see what they become. In approximately 2 trillion years, every galaxy outside the local group will have crossed that horizon permanently. The night sky will go dark. No evidence of the cosmic web will remain detectable. No ancient signals from the Big Bang. No gamma-ray bursts tracing the deaths of stars in distant galaxies. No light from 2 trillion galaxies blazing across the observable sphere. A civilization born into that era, however intelligent, however capable, would look up at a quiet, dark sky containing only the merged remnant of our local group and have no way to reconstruct what had once existed. They would inherit silence and call it the universe. They would be right, and they would be missing almost everything. We exist in the one window of cosmic time when none of that has happened yet. The filaments of the cosmic web are still illuminated. The ancient light from 2 trillion galaxies is still crossing the sky and arriving at our instruments. The signals from the first few 100,000 years after the Big Bang are still detectable in the microwave background. We exist not too early, when the structures hadn't formed, and not too late, when the sky has gone quiet, but in the precise era when all of it is simultaneously present and observable. We happen to be here, now, with telescopes pointed outward, in the one moment when the evidence is still visible. We are, among other things, very lucky. If you found this one worth watching, subscribe, there's more coming. Like this video if it landed differently than you expected, and drop a comment telling me where in the world you're watching from. I read every single one.